We're going to talk about Snell's law. This is always, to me, a fun lecture. Like I said, it's a fun one. This is the Snell's law, just like you quoted this morning when you asked about the class. But I'm starting with a little historical perspective. The Brachistochrone problem. Now, I say historical perspective. What I'm talking about now actually is after what we're going to get to with Snell's law. But brachistos is the Latin word to mean shortest, and chronos means time. So brachistochrone is the shortest time. And in June 1696, Johann Bernoulli challenged mathematicians to a problem considered by Galileo in 1638. What path provides the shortest time to go from point A to point B with only gravity acting on the object? Now, we can come up with some quick answers that are wrong. If I have point A and point B, I need to give myself space. Let's say here's A, here's A, here is B, and gravity is driving it. What path will take the least time to go from A to B? Let's start with something that is not right, but is at least thoughtful. Why is that not right?
Because gravity is driving, meaning that they might be falling at the same or different rates.
Well, gravity's acting vertically.
Right.
So it's the shortest possible distance, right. And we are going in a downward direction, which is necessary for gravity to drive it. But why is it wrong? What's the other thing besides distance that has to do with how long it's going to take?
Time.
Well, time is how long it's going to take. Yeah, the speed. So in this case here, you're picking up speed at constant acceleration, right? But if you pick up more speed earlier, you can cover a longer distance in less time. And so the shortest time path is not going to be the straight line. It's going to have to be something that goes down below. And so you might do like I'm going to do like this, go really fast and then go long. Well, that's not optimized. You're going really fast, but you have too long of a distance. So the real answer is somewhere in between there, something like that. Now, we want a mathematical solution, right? That's what
I guess that's what physics is.
Bernoulli asked in his challenge. Now, Galileo had made a mistake in logic and concluded that a circular path was the fastest. And Bernoulli had now solved it correctly, and he wanted other mathematicians to see if they could be as smart as him. Now, it wasn't just any old mathematician. Here's the correct answer. Solutions were provided by Isaac Newton, by Johannes' brother, Jacob. I would do the same.
That's a slap in the face.
Well, no, you can't let your brother be ahead of me, right?
Oh, yeah, of course not.
Yeah. Gottfried Wilhelm von Leibniz, you heard of that name before?
Not even a little bit.
Oh, you should have. It's a big part of this story. And William Francois Antoine Marquis de L'Hopital.
I've heard about that guy.
And I'm guessing, I don't speak French, of course, but I'm guessing we're actually supposed to voice the S in Francois because it's followed by a vowel. So maybe it's Francois Antoine.
Maybe.
I mean, they have, that's the rule. You voice the S if it's followed by a vowel sound and not if it's followed by a consonant sound.
So it'd be Francois Antoine.
But I don't know how you do it in person's name. That's different from... Anyway, that's not important.
Not important.
So, Newton's solution is noteworthy because Bernoulli, who was buddies with Leibniz, worked the challenge to tweak Newton. He put in words there that basically were kind of saying, yeah, Newton, you can't do this. Mm-hmm. Now, why would that be? Because calculus. Who invented calculus?
Newton.
Or Leibniz.
Oh, Leibniz, yeah.
Now, the way I understand things, of course, I'm not historically perfect, but my understanding is that during the Black Plague of what, I don't know, 1630, I don't know. During the Black Plague, Newton went home to Grandma's house, and he was working on his physics and realized there's no math to do these problems, so he invented his math of fluxions, which we now call calculus. And he wrote that he'd come up with a new math to help him do this. The end. Didn't explain what it was. So Leibniz came over and visited and said, hey, what is this math you're doing, this new math? And he explained it to him. And then Leibniz published it. And so Leibniz says, look at the math I developed. And Newton supporters, or Newton, what do you mean? That's the math I developed, I taught you.
Yeah.
The symbols we use, like the big S for summation integral, and the D for an infinitesimal, those are actually Leibniz creations.
Oh, okay.
So obviously, our calculus is heavily influenced by Leibniz. He published it. He made these symbols that makes it more workable. Newton, one of his specialities was not writing things that other people could understand.
Right.
So we can thank him for the calculus that we can understand in a reasonable fashion. But so there was a personal conflict, and so with Bernoulli being a buddy with Leibniz, he basically was pestering Newton with this. So Newton solved it in one night. It's not like he had to spend a couple months trying to figure this out. And when he sent in his solution, he includes statements that he did not appreciate being pestered by foreigners about mathematical things, because, math. So Newton came up with a pretty little diagram, but basically the shortest distance is this path here, which is called the cycloid.
How does that work? Oh, wait, they're all going from... They're going from C to B, P to Q.
So he takes the straight line that goes from A to B.
Right.
And then the cycloid that passes through the middle of that and through the point directly, I think it's directly above B. And no, it can't. It takes the cycloid, its bottom goes through there. Yeah, it should be directly above B, I think. And then, I don't know. I mean, He's got an explanation, a plan that works. Okay, so I didn't prepare that as historical perspective, which is really interesting.
Just wiping down
wiping doorknobs. Yep. Wiping doorknobs. My opinion, it's a fruitless effort. Somebody's going to open that door. Then somebody else, and then somebody else. And sure, you can clean it periodically, and you are cutting down some chances, but really small. I was asked today to clean the keyboards and on the laptops every day. Or not every day, but have a plan for it. I said, well, what about the desks? I don't know. I mean, you've got to wipe down the desk.
I mean, yeah.
After every class, if you're going
to... After I touch the laptop, I'm going to touch the Pasco thing.
Yeah.
I'm going to touch this. I'm going to touch the desk. I'm going to touch my paper. And then
basically, we need to sanitize everything between every class.
Right.
And of course, no lab partners.
Right. And plus with the whole doorknob thing, it's like, okay, so yeah, sure, we touched it not too long ago, and she just wiped it, but what about the people who cough in the hallway? Sure, it's going to take a while, but it's eventually going to get there. On top of that, what about the people that all enter at the same time and they all touch the doorknob one right after the other? Are you going to be like, hold up?
Well, you know what?
Hold up.
You actually have a good point. We should just prop the doors open between classes. Then only the teacher gets sick when he opens the door.
There you go.
But I hadn't even thought about it. That's a common sense thing, though.
Yeah.
So I'll do that from now on. I'll keep the door open before and after class.
I mean, honestly, yeah.
We're going to get it.
It is an issue.
Yeah.
But most everybody here on campus is going to be fine.
Yeah. Yeah, the only ones who are actually in any danger from this are
like
the old
55 plus or something.
Yeah. Anyway, let's not talk about me. Let's talk about you.
I didn't think you were that old.
I'm 53. But I've got only, 1/4 of my lungs are dead, which already puts me in a higher risk category. Okay, so the importance of the importance of this. So based on the discussion that came from this, Euler developed a method of variations they published in 1744 that Lagrange polished up in 1760. So this method of that's 50 years later. It's not like this was immediate, but this method of variations leads us to what we call Lagrangian mechanics, which is a really elegant and much easier generally way of solving problems than the methods you've learned. You learn Newtonian physics and you learn energy. Well, this is an energy optimization. As you can tell, that Lagrange is kinetic energy minus potential energy, right? So it's an energy optimization technique. And when I learned this in college, I was like, what? I could do all that work and I could have done this so much easier.
It is.
It is.
A lot more complicated.
No, it really isn't. Okay, so what you have is kinetic energy is a function of Q as a generalized position.
Okay.
It could be X, Y, Z, theta, phi. It's a generalized position. Q dot, that is the derivative of it.
Okay.
And then time. So for instance, you might have, let's just take Cartesian coordinates only. So you'd have kinetic energy of X, Y, Z, X dot, Y dot, Z dot, and T. Well, typically kinetic energy is only dependent on X dot, Y dot, and Z dot. But those are the variables you could use. And then potential energy based on the same. And then you just do partial. Remember, partials are the easy ones with respect to
QK.
Yeah, QK is like the first one, the second one, the third one. So could be X, could be Y, could be Z. Minus the exact derivative of the partial with respect to the same generalized variable derivative. So this is like partial of L with respect to X minus ddt of partial of L with respect to X dot. Equals 0. Gives you nice coupled equations, and then you solve the coupled equations.
You should probably write this down.
No.
Okay.
You don't need to know that. This is historical, and that's something for a higher level physics class that you're not going to end up taking.
I'm taking quantum mechanics. No.
Yeah, that's not high enough.
That's not high enough?
Well, it's different. Okay, different. Okay, so Fermat's principle. This is where we're going. Now you've heard of Fermat, right? Pierre de Fermat, the famous one. Fermat's last principle, I think, is what it was called. It was very famous. Maybe it's Fermat's last theorem. I don't know. But he had this thing where he said, I can easily show something simple. And he didn't write it down and he died. It was just in the margins he had written that statement, I can easily show this. And so that was in, he lived in the 1660s.
Right.
And, well, in the 1600s. And it was finally solved in the 2000s. Here's a mathematical genius.
Yeah.
It took over 300 years for somebody to actually prove what he said I can show symbols. Most people actually believe he must have made a mathematical error because the solution we have is not simple. Anyhow, so he's pretty famous in mathematical circles.
Yeah, no, I've never heard the name. So
in 1662, he wrote that light takes the path of shortest time to get from point A to point B. And the result can be that result can be inferred from Huygens' principle. If you take Huygens' principle, which is based on, each point on the wavefront is a new source of a wave.
Right.
And then you add up the wavefronts that it produces. Then using geometrical optics. I didn't show that in class because I was trying to get to other things that you actually are going to be tested on. Huygens' principle you can be tested on. Actually, Huygens, Huygens. It's either Huygens or Huygens. It's Dutch. Okay, so anyway, using that in geometry, you can derive Snell's law.
Right.
But using that same thing, you can see that it is, in fact, the path of shortest distance. So what we're going to do is approach this from the other side. Instead of approaching it from Huygens' principle, we're going to find the path of least time. And then say, is this in agreement? So that's what we're going to do today. So it's a Brachistochrone problem. It's not the Brachistochrone, but it's a Brachistochrone problem. And so let's get into it. So first, just so we can visualize things, if you are running to save somebody in the water, as a lifeguard, you have different paths you can take to get there. What do you suppose most lifeguards do?
Run straight to it.
Run straight to it. That's not what they're taught to do, though.
Really?
They're taught to run to a point right here. They're taught to run to the point where the water meets the shore straight out from the person, because that's the least swimming distance, because they're a lot slower at swimming than they are at running. So they're doing something close to the fastest path. The fastest path, they would be a little short of that. And you know what? They probably err on being a little short anyway. You know, you're trying to judge, and you're not going to overrun it, right? So they're probably coming very close to the closest path just because of human nature. Now, I was never actually taught to be a beach lifeguard. I was taught to be a lifeguard at a pool. Yeah, you're taught never touch somebody. Use something like throw them your can and let them grab it, and something like that, because that way you're not going to be drowned by somebody who's panicking. Anyway, so
I've heard there's a lot of schools about that. Anyway,
there's a lot of what?
There's a lot of schools about that. Like a lot of people are like, "This splash in the face, that doesn't work. Dump them a few times, and then if the worst comes to worst, knock them out." But no,
my teacher taught us, if somebody is grabbing you, punch them as hard as you can. That's what my teacher taught us.
I think that one too. I've never taken the life
because you don't want to be drowned by a panicky person.
Plus, it kind of knocks a little distance, and then lets you do your work. But,
This is way off topic, but it's not going to take us a long time to do this.
Yeah.
So here's the basic thing: if you cannot, throw them something, and if you don't have something like a towel or a shirt that you can have them grab to, so they're grabbing that and not you, then you come from that chair to there in front of them, stop. They will probably lunge toward you, and then you slowly go back towards shore and get them to get the shore on their own. If that doesn't work, if they tire out or if they're going down, then you very cautiously come in and try to rescue them.
Right.
And then if they're panicking too much, you punch them. Once they're knocked out, well, then it's easy. Oh yeah, just grab that arm, flip them over, lock them down, and away you go. Anyway, it's been a long time.
Lifeguards are violent.
I wonder do you know whatever happened to the guy who died in the swimming pool a couple weeks ago?
I didn't even hear about that.
Yeah, well, yeah. A couple weeks ago, a guy, the official report that Ryan Teller told Union College was that a person had a medical emergency in the swimming pool and was rescued by a lifeguard, transported to the hospital, where he later died, or where he died.
Okay.
What it said in the newspaper was that he was found unresponsive in the swimming pool and was transported to the hospital, where he was pronounced dead. And what it said in his obituary was he died doing what he loved, swimming at Larson Lifestyle Center.
That's a lot of stories.
I just want it to not be that he had a medical emergency and subsequently drowned. They were doing an autopsy, and I just don't want it to be that outcome. I want it to be
definitely not.
Either he was rescued, but was having like a heart attack and didn't survive the heart attack, or well, I won't.
Yeah,
something like that.
We do not want it to be he was swimming
and
drowning.
He was out there, and 5 minutes later, hey, you see that guy?
Yeah,
that would be bad.
That would be bad.
Because if you rescue in a timely fashion, you did the best that's possible.
Exactly.
It's all good. It's not good that a person died. You did the best that could be done.
But it's the best we can do.
Sometimes I wonder if I should put these things up on YouTube. So doing this problem.
Yeah.
And I forgot, I need to add 2 pages here, because, we're going to have to do some work. There we go. 2 pages added. here's our picture. So we have point A here that's P and point B that's P prime. Okay, so we're going from P to P prime.
Okay.
And we specify the distance between P and P prime is D in the direction parallel to the interface. And we are distance A in medium 1, a distance B in medium 2, perpendicular to the interface. So A, D, and B are all, for the sake of this problem, specified. In the end, we're going to solve this in terms of the angles, but for solving the problem, we're saying those specified, and then we'll just see how the angles come out from that. A, of course, is some distance x away from P, and that's what we're going to really try to solve for. What should I do if I'm going to try to do a Brachistochrone problem? Well, remember, Brachistochrone is trying to find the shortest time. So what do I need if I'm going to find the shortest time, if I'm going to minimize it?
If you're going to have the shortest time, you're probably going to need speed, distance.
Okay, speed is something I need. I need the speed. So mu1 and mu2 here actually are supposed to be the speeds.
Okay. Well, you've got time and you've got...
Well, I want to minimize time.
Yeah, you want to minimize time. So you've got speed and you've got a distance.
Mm-hmm. In fact, I'm not going to use mu's. I'm going to use V1 and V2. Right, I didn't make this picture. If I'm going to minimize time, what do I need? What do I need first? How do you, in using calculus, how do you minimize a function?
I do not remember.
You minimize by taking the function and finding where the slope is 0.
Oh.
And what's the slope in calculus terminology?
The slope is the derivative.
The derivative. So I need a function for the time first, and then I'm going to take the derivative of that function with respect to the variable. In this case, it's going to be x is the variable, and set it equal to 0 to minimize. So first I need to find the equation for time. So I have two times. I have the time in medium 1. And what's the relationship between time, speed, and distance?
Time is distance times speed.
So time is distance or speed.
Isn't it distance times speed?
Distance is speed times time. So if I divide both sides by speed, then I have time as distance over speed.
Right.
So time 1 is S1 over V1. Well, what is time 2 then?
S2 over speed 2, V2.
So my total time
is going to be S1 over V1 plus S2 over V2.
My variable is x. Where is x in this?
X is distance, so it's going to be S.
It's going to be in the s. That's right. So in terms of x, what is S1?
S1 is going to be, looks like it's going to be sine of theta 1.
I want in terms of x, not in terms of theta.
Oh,
We are going to get there eventually, but right now I want in terms of x.
okay, then total distance is going. Are you looking for S1?
Yeah, I'm looking for S1 in terms of a and x.
That's going to be the square root of x squared and a squared. X squared plus a squared.
All right, that is correct. What is S2 equal to?
S2 is going to equal the square root of d minus x squared plus b squared.
Okay. So now we can write this in terms of x. I'm not going to rewrite this though. You know what I'm going to do? dt dx is equal to d dx of s1 over v1 plus s2 over v2. Right, so I just did the derivative with respect to x on both sides.
Yes.
The v's are independent of x.
That is true.
So that's equal to 1 over v1 ds1 dx plus 1 over v2 ds2 dx. So now we just have to calculate the derivatives of s1 and s2. So I will maybe not.
There we go.
Copy these. Come down here to where I have more space. Paste them. And so ds1 dx. And how do you take the derivative of this bad boy?
Take everything. You're going to do a u substitution and raise to 1/2.
Okay.
Where u is equal to x squared plus a squared. Which means du, I'm assuming a squared is going to be a constant.
Yes.
Okay. So then that's going to be
Right, that's the chain rule.
mm-hmm.
So what is ds1 du1?
ds1 du1 is going to be 1/2 u to the negative 1/2. Or I guess it would best, yeah, there.
And then what's du dx1 or du1 dx?
That's going to be 2x plus 0. So just 2x. That's going to be 2x over 2u first 1/2. Which is then x over u to the 1/2.
Remember, u1 to the 1/2 is s1. Choose cancel. What is x over s1?
X over s1.
Here's, or s1 over x. I keep getting my ones in the wrong one. Here's x, here's s1.
That's theta.
It's not just theta 1. It's a trig function of theta 1. Which one? It's opposite over hypotenuse. Okay. I told you we were going there eventually, but not yet. We need it in terms of x initially. So we had one variable. We would have had two, theta 1 and theta 2. So there we have the ds1 dx is equal to sine of theta 1. Now let's do the same thing for s2. So if I do the same thing for s2, where s2 is equal to u2 to the 1/2 and u2 is equal to d minus x quantity squared plus b squared. So,
Hold up.
right, this stuff inside was the u.
Right, so u2 is the 1/2, and u2 is that plus b.
So what's the derivative of ds2 to u2? All right. Then we have to do the derivative of u2, the derivative of this with respect to x.
Right, so we got to do equal that. That's going to be. That's just going to be 2 times d minus x. Plus 0.
You got the minus 1 there.
Oh yeah, I did. I thought it was positive 1.
Because the derivative of minus x is minus 1.
Yep. And then the b is going to be 0, so that's going to be 2x.
Well, this was d minus x times minus 1. So that becomes minus d plus x when I multiply the minus 1 into the parenthesis.
What about the 2? Why doesn't that become negative?
I don't know how to answer that. You're just multiplying the entire thing by minus 1.
Right.
And so I could have put the minus sign out here, or I could have put it there. And what I have now is a whole mess. Well, you don't multiply every term. You multiply the entire side. Right. I took that minus 1 and multiplied 2. Okay, so what's 2d minus x? If I expand that, that's 2d minus 2x, right?
Right.
And if I multiply 2d minus 2x times minus 1, that's going to be 2x minus 2d.
And then
if I factor the 2 back out, it's 2 times x minus 2.
Okay, we're good.
It's a, I don't know, distributive, commutative, I don't,
It's something.
yeah.
One of those basic things from way back when.
Okay, so that derivative is 2 times x minus d.
So then we're going to have x minus d over u2 to the 1.
And since S2 is U2 to the 1/2, that's S2. Of course, the 2 over 2's cancel. And so if we look up here, x minus d. Well, this here is d minus x, right?
So is it in the reverse? No.
So which side of the triangle is that? The d minus x?
That's bottom.
Yeah, so opposite adjacent hypotenuse.
That's opposite.
Opposite. So opposite over hypotenuse is,
Hold on. We have x minus d, not d minus x. Oh, okay. There we go. So then opposite over hypotenuse is once again going to be sine, so it's going to be negative sine.
and so,
Can you scroll down so I can get that
yeah, my work is going around in circles, isn't it?
a lot? Yeah, right. So that actually okay. Okay.
So here is what we've done. I've just summarized what was shown up above. So the ... is this stuff right here.
Right. Okay, so
And the work that ended with this result. Or excuse me, it ended with this result.
right.
And the work that ended with this result.
Now, how do we go from 1 over velocity to n?
Definition. So let me do one step first, and then I'll do that. Don't worry. That one step is simply adding the one term. So this becomes, with no hard thought, 1 over V1 sine theta 1 equals 1 over V2 sine theta 2.
Yes.
Now, to get this to Snell's law, I do this magic step. I multiply both sides by a constant c, speed of light in vacuum. And it's magic because c over V1 sine theta 1 equals c over V2 sine theta 2, with the definition that n is defined as c over v, then this is n1 sine theta 1 equals n2 sine theta 2. I knew you'd recognize it when I said it.
Yeah, I have that just like that.
And so there we have it. We have shown that if we were to take Fermat's principle saying that light takes the shortest path possible to go from point A to point B, then we end up with Snell's law. Now, I'm actually done, except for I want to go back and make sure that we have in our heads reality and not just math. So the example with the lifeguard was trying to go from point A to point B. Real life situation, if I have a light bulb here at point P, what is the light doing? Forget everything else, just say I have a light bulb at point P.
At point P. At point P. It's sitting there.
In what direction does the light go?
All over the place.
That's right. That's the key. I want to make sure we remember, we don't forget. The light is going everywhere. And so what we calculate is, for the ray of light that goes from point P to P prime, it's going to follow this path. But it's going to follow all kinds of paths going all over the place. Because sometimes we get so locked in. We do this problem, we're like, yes, well, the light just goes here. Well, why does it only go here? Why doesn't it go anywhere else? Done. We were just calculating what it is. Right. So I just want to make sure we have that, squared away. We're not thinking, wow, it's really miraculous. How does the light know that it needs to go to point P prime?
Light goes up. I mean, I don't if it worked that way, all it would be just a single ray, a single dot of light.
I have to be to the right place to see anything.
Right.
Mirror only makes
a single dot of light right here below the light bulb. Yeah. That doesn't happen. So obviously,
I myself have been in situations where I'm like, wait a minute, and I forgot what was really going on because I just got into doing the math. Kind of like I was talking about in the test, the problem, everyone missed. I'm pretty sure people knew the concept, but they didn't think about the concept. They just said, oh, what equation goes with this? Put numbers in. And we have to take a bigger picture approach. We can't just say, oh, we're putting numbers. That's not what we do in physics. We analyze situations. Right. Okay, we're done.
Early lunch.
Yeah.